Hi, my name is Timothy Coolong. I'm a professor of horticulture at the University of Georgia, and I'd like to talk a little bit about biochar today. The point of this talk isn't so much to convince you yes or no to use it or not, but I want to provide some scientific background about biochar, some of the pros, some of the cons, and where it might fit into your production system and so forth. So biochar comes from the term terra preta, which is literally dark earth. And so terra preta is found primarily in Amazonia and some other regions, typically tropical areas. There's parts of West Africa where it's been found. And basically it is incompletely combusted biomass that's in the soil that was left there by cultures, indigenous peoples thousands of years ago. And so basically, different cultures settled in small communities and they would have fires and so forth. And over time, the incompletely combusted biomass of those fires went into the soil and stuck around, and it's what you see today. Now, there's some anthropological evidence to show that at first this was just, pretty random and so forth. But over the years, the indigenous people understood that this dark earth, this land was much more fertile and crops did better. And so in the latter part of some of these civilizations, there's evidence to show that this incompletely combusted biomass was deliberately placed in fields. And so, and because it's still around today in these historically poor soils, and they still remain fertile, this is something that where this carbon has never been, obviously some of it's been leached, but it hasn't been leached out. And so it's remained for thousands of years. It's very stable. And so this is kind of where the concept of biochar. Now, biochar and terra preta are different things, but the purpose would be the same, to add kind of a very stable carbon to your soil to improve soil fertility, soil quality, and so on. And so biochar is basically a very carbon-rich material produced through pyrolysis. And some of you may be familiar with pyrolysis, particularly if you're viewing this video. But for those who are not, it's basically heating an organic material in the absence of oxygen or very, very low levels of oxygen, typically between 300 and 1,000 degrees C. Usually it's a little less than that. And then from that, you get syngas, heat and power, different types of bio oils, and then biochar, which is kind of the solid remaining product from that. And so there's a number of different companies that make biochar today, but that biochar that comes off from that is a very stable product that can be used then as a soil amendment. And so thinking about biochar, there's two main things that affect kind of the properties of biochar. Going back to our previous slide, you can see you've got feedstock and then temperature. And those are the two things that impact kind of the qualities of that biochar. So what your feedstock is, and then whether it is slow or low temperature pyrolysis or elevated. Typically temperatures from most of these processes are between about 330 and 700 degrees C. But as your temperature of pyrolysis increases, your pH of your end product increases, the carbon content increases, surface area and porosity increase up to a point. And the reason for that is once you get to really high temperatures, the porosity does increase. There's a lot of micropores, but in terms of kind of agricultural applicability, these micropores are very, very small and they may not contribute a lot to the properties in the field. But nonetheless, as you increase temperature, surface area does decrease, and then nitrogen content decreases. So just for those, if you're interested, there are lots of resources online about how to make your own pyrolysis and biochar kind of production system if you'd like to. If you don't want to buy it, you want to do it yourself. This is a picture from a publication at Oklahoma State that shows how to make it on a homemade scale. If you look online, you see some people with huge homemade biochar facilities. But basically, the reason I chose this picture is because it kind of shows how you would go about making it, right? So you have a 30-gallon barrel in the middle that's kind of sealed up. It's got a vent on it so it doesn't explode, but that's your low oxygen environment. And then around that, your 55-gallon barrel is where you put your fuel. In this case, could be wood or any other thing to heat it up. And so this is essentially how you would do pyrolysis. I worked with a colleague at a university in Jordan, actually, and we built something very similar to this in terms of how to make biochar. So as I mentioned, temperature and feedstock is very important. And I want to spend a few minutes here in the first part of the talk talking about that because you can see very different effects if you put this in your field. And so, some people I think that I'm going to talk about differences in terms of yield from different biochar trials. And a lot of that may have to do with differences in feedstock and the pyrolysis process. And so this is actually some work that was done at the University of Georgia back in about 20 years ago, actually, by Julia Gaskin. And this was done in South Georgia in Tifton, looking at locally available feedstocks. So peanut hulls, we got a lot of peanuts in Georgia, sawdust, pine chip pellets, and pine bark, because we have a very large timber industry, and then hardwood chips, which we actually don't have a lot of hardwoods in South Georgia, but for the other ones we do. And so these are the different classifications of feedstock we had. And then if you look at char temperature, which is kind of the first column in that table, you'll see 371, 402, and 426. That's the different temperatures at which pyrolysis was conducted. But the real point of this, I wanted to show you, if you look over here at the carbon, you can see there's some, subtle differences, not huge. Sawdust is 71%, peanut is 68, 65. But if you look at nitrogen, you can see some very large differences. And this makes sense, right? Peanuts are legumes and so forth. They're cropped, so they're going to have more nutrition in them. So the peanut hulls that are used, if you were to then use that as a biochar in your field, you're going to get a reasonable bang for your buck in terms of nitrogen. Whereas some of the other products like the pine bark, you're simply not going to get that. Likewise, if you look over on the right side of the table towards potassium, again, peanuts being a cropped system versus the other feedstocks, you're looking at 6,000 milligrams per kilogram in terms of potassium content. And so again, you're going to get a lot more out of that than some of your other feedstocks. And then this is actually from a review paper that looked at not just stuff used in Georgia, but a wide range of studies that were done with different feedstocks and different temperatures. And so I put this again in here just to demonstrate the large differences. So you see there orchard pruning. So if you were pruning a peach orchard or an apple orchard, you could use those cuttings from the wintertime and make biochar out of them. You can see they had about 77% total carbon when pyrolysis was conducted at 500 degrees and so on. You go down to canola straw, and there's a study that did several different temperatures of pyrolysis, 300, 500, and 700. And you can look at like total nitrogen. It actually decreases as you go up in temperature, which makes sense that nitrogen burns off. But this is kind of surprising. If you go to the middle of the chart, you can see the C to N ratio. So, I do a lot of cover crop work, and typically we're aiming for like a 30-to-1 C to N ratio and so forth, so we don't tie up residual nitrogen. But surprisingly, the canola straw, look at that, 1,600-to-1, basically C to N ratio. And that varies. Surprisingly, it was a lot higher than even wood. And so, again, you're going to have very different responses. If you put out 20 tons an acre of biochar that's made from that canola straw, you're going to have a very different crop response, perhaps, than if you're using orchard prunings or corn straw or what have you. And so keep that in mind. If you do purchase biochar, try to find out where the feedstock came from. So I also wanted to show you biochar has been known to increase pH. And this work here was done by a colleague in our department at UGA. Her name is Ping Yu. She's our nursery specialist. And it was work, actually, it was looking at tomato and basil in containers, and she used hardwood and sugarcane bagasse biochar. So the hardwood biochar on both graphs, you can see it's the triangle with the dotted line or the dashed line, and the sugarcane bagasse biochar is the circle with the little dotted line. And this looks at the first one is pH, and the second one's EC. So I wanted to point out a couple of things. In this graph, you can see that pH does increase significantly in the container as you increase biochar. But if you look at the incorporation rate, you don't really see a big increase until you hit 50% or more, which is a lot. If you're adding biochar to a container system, you probably wouldn't add it at an amount greater than 50%. And so while yes, it does increase pH, that is certainly true, the effect, particularly in a field, is probably going to be minimal because you're not going to be incorporating it at such a high rate. The same thing with EC. So EC is your salt measurement, your salt levels. Again, they do increase to levels that would, impact plant growth, but you're probably not going to incorporate them at such a high level in your field. You're not going to, put 80% of an acre furrow slice of biochar. So again, for most of our practical purposes, these things should, while it may have a slight liming ability and so forth, they're going to be very, very minor. And so I did want to point that out because a lot of the studies that are done are container trials. But if you're using this in the field, like if I do field vegetable production, it's probably not going to have as significant an impact. And then lastly, I kind of wanted to wrap up with different feedstocks, and this is some electron microscopy of the different surfaces of the biochar. And so remember I talked about porosity before and bulk density and those sort of things. Well, if you look at the different biochars based on feedstock and temperature, you can see obviously the surface of these biochars is very, very different. And so in the top left, that's biochar from tomato stalks and so forth. But then right below that is poplar wood biochar. And so it's got very different characteristics. And then to the right of that is miscanthus, so that's a grass. And again, its cell shape is different. It's going to have different porosity. On the right side is the broccoli-based biochar that Dr. Moawesh and myself worked with. And you can see that it's got very different surface characteristics. So again, just showing you that at many different levels, your feedstock is important. So a couple of things on biochar applications. Typically, application rates are quite high, usually from 20 to 50 tons an acre. And most studies are in the 10 to 20 ton per acre range. So if you're used to putting compost out at 10 tons an acre, that kind of gives you an idea. I will say that biochar is not very dense. It's kind of light and fluffy. And so putting out 10 tons an acre of biochar is probably going to look like a lot more than 10 acres of 10 tons of compost. And so this photo is from Dr. Ted McAvoy. He's down on our Tifton campus, and he was doing directed biochar applications to his plant beds, and then he would come back through and put plastic over this. And you can see by some of these, the darkest bed there, that's 20 tons an acre. So again, it's more concentrated because it's not broadcast, it's fitted to the bed, but it just goes to show some of the rates that are used are very high. And then keep in mind, I just showed you some data from pot studies where they were looking at 3 to 5%, or in those cases, it was 50%. If you look at that on an acre basis, that's 30 to 50 tons an acre. And so some of these studies, I want you to be educated if you're reading some of these to just realize that some of these rates where it's applied are quite high. In Georgia, we have a couple of sources of biochar on a large scale, and they run 140 to $176 per metric ton delivered, so 2,200 pounds. I am not sure about North Carolina in terms of sources of biochar. This would be if you were in South Georgia, so if you don't have a source nearby, it's probably going to be a little bit more expensive. So if you look at that to apply some of the even the lower rates, right? If you're looking at 5 to 6 tons an acre, potentially you're looking at $1,000 an acre on the low end. And so it is a significant investment that you have to think about if you're going to use biochar. If you go out at a very low rate, and I'm going to talk about a study I did in a minute that was done at low rates, it can work, but it's kind of nuanced. Um, do consider, though, that biochar is very stable. Remember that terra preta slide? Some of those are thousands of years old. So it is going to be very stable in the soil. So if you do put out large amounts, it should stick around. And I will say that I think the sieve size is important. Having put out biochar numerous times in trials, if you get a very, very fine particle size, as you can see the picture at the top here, it's actually kind of hard to apply because it is very light and it's not dense. It blows around quite a bit. I've used cone spreaders, manure spreaders, done it by hand. It can get pretty messy. And so I just tend to like more of the larger size. That will give you fewer sites for like microbes and nutrients potentially, but it's a little bit easier to manage if you're applying it. So I want to talk a little bit about yield, and then we'll wrap up talking about some of the effects on soil. So I've done a few yield trials. I'm going to highlight them, and I'm also going to talk about some review papers that talk that cover hundreds of other trials that have been done on yield. And so again, the implications are varied. Your source, your rate, and the crop were all important. This is a picture of a radish trial that I did while I was in Tifton with a company. And this was very interesting because the company wanted to use a very low rate of biochar. Instead of a large broadcast application, they wanted to use a 2x2 offset. So a lot of row crop farmers will use a 2x2 offset when you're planting. And that offset, typically you'll put up fertilizer or something, and it's just off of the row of the planted row by 2 inches, essentially 2 inches down and 2 inches off to the side. And so we did this with radish. And the idea being, one, we wanted to make sure it didn't negatively affect the plant. And then also, could you see a benefit from a small targeted application? So these radishes were grown conventionally. They were fertilized heavily like you would for radish that you want to get out of the ground really quickly. This was done in Tifton, so it's a sandy soil, much like your coastal plain in North Carolina, low organic matter and so forth. And so you can see there with the ruler, we're kind of where we put the biochar offset. So this is just a shot of the trial right after seeding, a few days later after emergence, and then the radish coming up. And then those are some of the harvested radishes. But with that placement, one of the things, again, we were interested in was would there be any negative aspects to it? And we did not see any. You can actually see in this picture, it might be kind of hard, but you can see at the bottom of the radish, there's little chunks of biochar attached to the roots. So they grew right through that band, essentially. And so we had no negative effects. Again, this is a very low application rate. It wouldn't be common. And I want to reiterate, after this crop is out of the ground and you disc it up, it's going to be spread out. And so it would probably be at too low a rate for subsequent crops to have a positive impact. But the way it was applied actually did work. And so there's a lot of data on this slide. I don't, I hate to put this much data out there, but basically our control treatment is number one, it's at the bottom. And here you'll see the yield. And this is bags, 6-ounce bags of radishes per acre. So if you were a commercial radish farmer selling them in little bags, it would be in a 6-ounce bag. And so we saw about 5,000 pounds an acre of yield. And this was significantly different. Again, the p-value is 0.08, but if we used a zero point 0.1 value, it was significantly lower than many of the other application rates. And so we did see a yield bump from some of these applications. The different treatments here are all different sieve sizes and sources and so forth, and there wasn't a lot of consistency there. But I did want to point out that it did work. It didn't have a negative effect. It's a very unique situation, the way it was placed, but it might be something worth considering. We also have done work with spinach. We saw a less dramatic effect. This was we did different rates. Again, these are pretty low, 600 pounds banded in a bed, 4 inches below. This would be, these other rates I'm talking are 10 or 20 tons an acre. So this was very targeted, very low rate. We did see a slight bump in yield on some of these, but I would say there's a little bit more variability compared to the radish trial. And then I did want to point out there are literally thousands and thousands of yield trials out there. A good colleague of mine, Ajay Nair at Iowa State University, did a multi-year trial with potatoes. He did not see a significant difference. He looked at scab because he was concerned about the pH effects, saw no difference in scab. And so there are some trials that show no effect, but then there are just as many that show a positive effect. And so this here was taken from a review paper. And basically, it analyzed hundreds of yield trials in biochar. And they kind of split up yield into different classes. And so for the top of this square graph here, they looked at high temp or pyrolysis temperature and carbon content. And so if you look at this graph, the red line would be the fertilized control. So that's no biochar, it's just a regular plant. That's your control group. And then they split the different studies into a low temperature, low carbon, high temperature, low carbon, high temperature, high carbon. And what they found was in those studies that used a low temperature pyrolysis with a low carbon product, they basically had no difference from the control groups. When you had a high temperature, high carbon product, in those studies, the yield was on average probably about 17 or 18% better. So again, it just shows how you could look at two studies, one says it doesn't work, one says it does, but chances are there's a big difference in the feedstock and pyrolysis temperature. The second part of this figure, part B, talks about nutrient content and carbon content. So this paper looked at nutrient-rich biochar, which is those that come from manure and sludges, which realistically, we're probably not going to use much of those in the United States. And then what they've considered poor nutrition, which would be wood and plant-based biochar, and that's going to be much more common in the US. And so what they found, so if you look here, poor nutrition, high carbon, those studies tended to have a positive benefit. Poor nutrition, low carbon, so again, poor nutrition means wood and plant-based, it overlapped with the fertilized control. So there were probably a number of studies that didn't show an impact. The highest bang for your buck was rich nutrition, high carbon. But again, this would include things like sewage sludges, which we're not going to use, even if it's in a biochar type system. But that's where a lot of the studies, they get the biggest bang for their buck. And then the rich nutrition, low carbon. Again, it's much more similar to the control. So it looks, for the most part, in the United States, we're going to be using wood-based products, which would be considered low nutrition. But if you go for a high carbon percentage and high pyrolysis temperature, the chances of you having a positive effect, again, because it's going to have higher porosity, more carbon for the soil, and so forth, is going to be there. So lastly, when I talk about all these studies, there was a very recently published study out of UC Davis in California. And it was a 3-year processing tomato study, and they put out biochar at about 1.8 tons an acre. It was an almond shell and softwood biochar. And so that would be kind of poor nutrition, high carbon, reasonably high temperature, 500 degrees C. And they found there was no significant impact on yield. But there was a very positive impact on soil health, including pH, EC, soil potassium, and aggregate stability. And so that's kind of what I wanted to talk about. Even though you may not see big yield benefits, there are going to be potentially benefits for soil health. Now, you as a farmer need to decide, is this going to be something I'm incorporating into my farming system to improve soil health? And down the road, you may improve yields by doing those things that we always talk about, improving organic matter, nutrient holding capacity, and so forth. And so I wanted to spend the last couple minutes here talking about biochar as a soil amendment and what it can do if you focus on kind of the soil building properties. So biochar, we mentioned, increases cation exchange capacity, so it's going to hold nutrients a little bit better. Biochar does contain some nutrients. I showed that slide at the beginning of this that had peanut hulls in it. Usually what we see is there's kind of a quick flush of a little bit of nutrition, and then the rest of those nutrients are very tightly bound. So it's a very slow release after that. One of the good things it does is, in general, biochar will decrease bulk density. So decreased bulk density usually means that there's more porosity in the soil. And it's also been shown to increase aggregate stability. And this is something, this picture, I actually show this picture in my organic ag class that I teach here. And aggregate stability is one of the important things for measuring soil health. And often we talk about adding organic matter, so adding compost, cover cropping, and so forth to improve aggregate stability. And so biochar can also do that and has some of those properties. And then also microbial activity. Biochar, because you can see in this diagram here, it's very porous. It offers a lot of sites for microbes, and it has a lot of sites for nutrition, for nutrients rather to bind, and also mycorrhizae, fungi can colonize that biochar. Often, studies have shown there's a kind of a quick increase in microbial activity after a biochar addition, although not always. But what's interesting is pyrolysis temperature was the biggest factor determining that. And counter to a lot of the other things, at the lower pyrolysis temperatures, carbon was a little bit more labile. And so you had kind of a greater flush of carbon that was increasing microbial activity right after that. And then it drops off and so forth. So again, it can help do these other things in the soil, much like adding organic matter from other good farming practices. There are some potential negatives that I did want to highlight because you are taking a feedstock and you're concentrating that through the pyrolysis, through the actions of pyrolysis. If your feedstock contains a lot of heavy metals, they do become concentrated. With that said, most of the feedstocks that we're using, if you're using like pine bark for a feedstock, if it's coming from a large pellet facility or something, they're not going to have a lot of heavy metals. But if you took feedstock that was like a sludge-based feedstock, then that could be an issue. They can also contain hydrocarbon contaminants. And so that's something, again, that's very much feedstock and pyrolysis temperature driven. Although if your feedstock potentially is contaminated, your pyrolysis temperature, you're still going to have polyaromatic hydrocarbons. It'll just kind of change the type that you have. Again, I wouldn't say these are overwhelming negatives or anything like that, but I did just want to make you just aware of that. So conclusions, some of the data on yield is very mixed. In general, I would say the impact on the soil is positive, and it is a very stable way to fix carbon in the soil. But as I said, throughout the study, it's very much affected by feedstock and pyrolysis temperature. And I would encourage you, like my previous slide, I talked about metals. If you're going to buy a lot of biochar, make sure there's an analysis that goes along with that. And so I think it can be part of your soil management strategy on your farm if the cost is acceptable to you, right? It's an off-farm input, and so it's going to be a cost to you. And so if that works for you, then great. But hopefully this information can be useful to you. In the presentation, I have citations for all the papers that we pulled data from, so you're free to look those up on your own if you like. So with that, I'd just like to say thank you.
Thank you, Tim, for being willing to present a very timely presentation on biochar. So with that, I'll ask Rachel if she has any questions. I know I had one that I know a lot of growers have been asking me about using biochar as an amendment as it relates to Hurricane Helene impacts on areas where we've lost a lot of our topsoil and organic matter in soils. So could you speak to maybe some of the pros and cons of maybe using like a portable system to maybe process debris related to the storm, and maybe some pros and cons to that, and maybe some things to think about as it relates to that specific stock material?
Sure. So I think in the mountains after Hurricane Helene, there's lots of debris, so there's lots of feedstock available, and I think that certainly doing it on your own farm, if you build your own system, or work with your neighbors to create this, I think um, obviously there's going to be some differences in biochar because the feedstock is going to be different from one location to the next, right? But I think overall, if you look at it as, I'm not necessarily putting this out simply because you know, I think if you step back and look at, in the hurricane situation, a lot of the soil was just washed away completely. And so it's not as if you've got this field that you've been growing corn in and I'm going to add biochar and see if I get a yield bump. It's more of I'm really trying to rebuild my soil from the ground up. And so I think in that situation, the feedstock isn't going to be quite as critical because you're just trying to build organic matter, build soil carbon, and kind of push your soil in that healthier direction. And so I think it can be effective. If you lose, 6 inches of good topsoil and you're just dealing with the B layer of soil, um, it's probably going to take more than just biochar. I think it'll just be one tool to help. But certainly with the amount of debris that's there, if people want to do this on their own, they could build their own type of pyrolysis reactor. So I don't think it's essentially a bad thing. I just think that it's going to take a while.
Awesome. Rachel, did you have any questions?
No, not at this time.
Okay,
Thank you.
cool.
Great presentation.
Yeah, this
Cool.
is awesome, Tim. Thanks again for being here. And with that, we'll conclude the video.
Great. Thank you so much. Thanks for having me.